We propose a few short semi-supervised learning framework for scalable labeling of data in the wild. We do this by exploiting the temporal nature of the captured video sequences along with geometrical consistencies of the given object. The data collection and annotation has traditionally been addressed using these huge multi-camera rigs. However, this is an extremely complex and expensive setup and not suitable for in-the-wild data labeling at scale. Relying on such rigs, we have made substantial progress in labeling categories such as humans or hands. However, annotated datasets for long-tail distribution categories such as these animals casually captured in the wild is largely out of reach. For such scenarios, triangulation is not possible and hence no reliable solution exists. Our approach only needs 2D annotations for 1 to 2% of the video frames. The outputs are recovered 3D and 2D labels along with the confidence flag for those labels. To this end, we also release MBW zoo dataset that is collected in the wild with 2 handheld cameras. To be more specific, given 2 view videos, we annotate 2D landmarks on 1 to 2% of frames that are chosen via uniform sampling. And as an output, we generate the 2D and 3D landmark labels for the entire video. Naively solving this problem, if we train a deep neural network over 1% of the frames, we see that sample complexity is too low to train such a deep neural network. Leveraging the temporal consistency though, we could use optical flow to propagate 2D labels from the initial 1 to 2% of the labels. Optical flow would eventually face failure due to occlusions or image artifacts. However, it will at least give us enough inlier labels surrounding the initially seeded labels, increasing the sample complexity to eventually use a deep neural network. To do this at scale though, we need to find such inliers without human intervention. And we do this by using the 3D information, which is learning a statistical shape distribution of the object category. Let us assume an oracle gives us the shape code that generates plausible 3D structures. Such a 3D structure, when projected into 2D, could help us detect the 2D outliers. But how do we learn this shape code psi? We learn this psi by enforcing low-rank shape prior on the 3D structure S, where S decomposes into a dictionary D and a code psi. This D consists of many such non-rigid deformations. In this prior, each code is represented by a sequence of dictionaries and corresponding codes hierarchically. Let us term this as equation 1. Connecting this prior back to 2D projection, we know that we can obtain the 2D label by projecting the 3D structure on a camera T. Applying this operation on equation 1, we get the above setup. Because of multi-layer hierarchy, we formulate the right-hand side as an encoder whose output is termed as psi as shown here. Using the above, we can learn this neural shape prior psi by this 3D lifting framework. For more information, please have a look at the 3DV 2021 paper mentioned here. But are 1 to 2% of frames enough to learn a good 3D structure that drives this MBW pipeline? While it is not enough to learn a perfect 3D structure initially, it is enough to learn a reasonably plausible 3D structure that rejects the most egregious outliers at a very conservative threshold. We validated this by running experiments on a dataset with ground truth 3D. In spite of only using 2% of 2D labels, we are able to achieve 3D performance comparable to those using 100% of 2D labels. Looking back at the pipeline, we can now use this neural shape prior to reject the outliers from flow predictions. Thus, along with predicting flow, we can learn this 3D lifting framework in parallel. Once psi is learned, we freeze its weights and pass the 2D flow predictions to the lifting network. Since it only outputs plausible 3D, when reprojected into 2D, it detects the outliers from the flow predictions. Thus, our 3D lifting network acts as an out-of-distribution or OOD detector. With the inliers obtained from optical flow, we can now retrain psi and extend the distribution space of lifting network. With enough sample complexity, we can now use a 2D DNN and carry out the exact same setup as the previous one, replacing optical flow with deep neural network. In this way, we can iteratively run this bootstrapping pipeline and increase the inliers in each iteration. Visualization of 2 dimensions of psi shows that as the iterations increase, we increase the amount of inlier annotations. If we are left with a contiguous chunk of outlier frames at the end of all iterations of MBW, we can explicitly send them for manual annotations, opening an avenue for cost-efficient active learning. We validate the labeling approach over a publicly available cheetah dataset with ground truth. We also show human dataset results in the paper. We also release a zoo dataset consisting 2D, 3D landmarks and bounding box labels. A note on limitations of MBW. MBW is prone to face mode collapse, usually seen in GANs, if the initial 1% of labels do not cover enough non-rigid pose variation. Thus, MBW carries out OOD detection and auto-labeling for data captured in the wild in a few short fashion. We release the code along with the dataset. Please have a look at the project page and paper for more details. Thank you.